He heard a sharp metallic crack. The anchor chain had started to run free. The sound, sudden and impossibly sharp, cut through the low-frequency rumble of the 65,000 DWT bulk carrier MV Argonaut wrestling with the North Atlantic swell. Chief Mate Eric Jensen, positioned near the port hawsepipe, immediately felt the sensation through the steel deck plates, a grinding vibration, momentarily overriding the heavy pitch and roll. The Argonaut, loaded with iron ore concentrate, was en route from Septiel to Rotterdam, but had been forced to anchor for shelter near the Grand Banks 4 hours prior. They had dropped the starboard anchor in 35 fathoms using 7 shackles of chain, approximately 210 meters, to hold the vessel steady against the worsening conditions. The weather had deteriorated rapidly from force 5 to a steady force 7 on the Beaufort scale, with occasional squalls pushing it to a dangerous force 8. The vessel lay exposed to beam seas and a quartering wind, creating violent surging motions that constantly tested the anchor gear. Jensen's current position was the port side of the forecastle, conducting his 5th scheduled hourly inspection since dropping anchor. With him were Boatswain Thompson, a meticulous man with 20 years of deck experience, and an able seaman, A.B. Miller, who was standing by with a portable air-powered wrench. The standard operating procedure required continuous monitoring in conditions above force 6 due to the high probability of fatigue or creep failure within the securing arrangements. The port windlass station was identical to the starboard side, a steam-driven triple-spool unit designed for 2 170 Lemuel U3 chains. The crucial components under observation were the wildcat, the segmented drum that engages the chain links, the surrounding brake band, and the chain stopper. The Argonaut utilized a common high-holding power pile stopper, a heavy-duty cast steel block that, when engaged, takes the primary horizontal load of the vessel, preventing it from bearing solely on the windlass brake. The anchor chain itself, made up of standard connecting shackles and 27.5 meter lengths, disappeared into the dark, flared opening of the hawse pipe. Jensen walked around the pedestal of the steam windlass, his hand checking the heat of the brake housing. The brake was set hard, the lever pulled fully against the maximum position, and the heavy steel band clamped tightly around the rotating surface. In heavy seas, even when the pawl stopper was engaged, it was standard practice to keep the brake tight, ensuring the chain could not run if the stopper failed, and minimizing any unnecessary play in the system. The first subtle warning sign had registered an hour ago. The brake housing was noticeably warm, not hot enough to cause immediate concern, but warmer than the ambient sea spray-cooled steel. This heat was the mechanical energy of the surging ship being converted to thermal energy. Every violent lift and fall of the Argonaut, our dower, pulled the chain taut, slightly stretching the steel and attempting to draw a few centimeters of chain through the wildcat. Despite the enormous clamping pressure of the brake band, this minute slip generated friction. Thompson pointed toward the chain, which was entering the wildcat. "Chief, she's humming again." Jensen knelt to listen. It was a faint, low-frequency sound, a metallic humming that seemed to originate from the tight, almost vibrating chain sections held within the wildcat segments. It was the sound of molecular friction, the constant high-tensile stress oscillating in the chain links as the vessel lifted and dropped 20 feet. This vibration suggested the load on the chain, transmitted through the pile stopper, was exceptionally high, possibly exceeding 70% of the working load limit. The ship was trying to walk the chain, link by link. "Miller, crank down the brake nut 2 full turns. Bosun, check the dog on the stopper. Make sure there's 0 daylight under that pal," Jensen instructed, his voice flat and steady against the wind. The language was procedure, not panic. Miller applied the wrench to the large tightening nut on the brake assembly. With a deep grunt, he forced 2 more rotations, compressing the springs and increasing the mechanical pressure on the friction material inside the brake band. The increase in pressure was marginal but psychologically important. Every layer of defense mattered. Thompson, using a steel bar, carefully tapped the large locking pin of the pile stopper to ensure it was fully seated and engaged against the link it was holding. The stopper was the true failsafe. If it failed, the full dynamic pull of the 65,000-ton vessel would transfer directly to the windlass brake, which was only designed for static holding and initial snubbing, not repeated high-impact loads. The vessel took a particularly vicious shear, a sudden lateral swing combined with a drop. The chain line, which had been tight, momentarily slackened, then snapped taut with a sound like a pistol shot being fired inside a steel drum. The entire windlass frame shuddered. It was immediately following this impact that Jensen heard the first sound, the sharp metallic crack. It wasn't the wildcat itself, nor the chain. The sound originated from the heavy cast steel frame of the pawl stopper, specifically the small high-stress load point where the frame bolted to the deck structure or where the locking pin seated against its support. Thompson swore softly, a quick professional exhalation. "The dog," he hissed. It slipped a quarter-inch. A quarter-inch slip meant the immediate sinkering force had momentarily lessened, allowing the enormous stored energy in the chain to jolt forward. It meant that the primary safety device was now compromised and likely carrying the load inefficiently. Jensen watched, his vision narrowed to the small, crucial gap between the chain link and the powel, noticing a fresh layer of powdered rust. Dust, evidence of metal shearing under stress. The subtle warning signs had now coalesced into a clear diagnostic. The anchor gear was at the limit of its mechanical integrity. The brake housing, now smoking faintly with moisture vaporizing off the hot steel, was secondary. The stopper was the point of imminent failure. Jensen reached for the emergency steam valve actuator, ready to flood the brakes with water cooling, and shouted, "Miller, stand clear of the chain. Bosun, get the crash bar ready for manual override." Before the bosun could fully react, the Argonaut crested a massive wave, paused weightlessly, and then plummeted into the trough, accelerating forward and down. The sea state had escalated violently. The chain went from taut to hyper-taut, stretching infinitesimally along its entire length. This time the sound was not a crack, but a sustained, tearing shriek of metal failing under tensile load, accompanied by a sudden release of pressure from the tightening nut on the windlass brake housing. The retaining structure of the brake band had yielded. The full load was now on the compromised stopper, which was screaming its own death knell. The chain was no longer vibrating. It was lunging. The wildcat, despite the tightened brake, began to creep, turning slowly at first, gathering speed as the friction was violently overcome. The pawl stopper, the final safeguard, had reached its limit. Jensen saw the heavy steel dog buckle sideways just as the wildcat began its high-speed rotation. He shouted one word into the wind, "Run!" The word "run" was drowned out by a sound that instantly defined the disaster. The uncontrolled roar of 200 meters of heavy anchor chain tearing through the hawse pipe. The pawl stopper, having held the immense dynamic load of the Argonaut for 4 grueling hours, had finally failed catastrophically. The steel support bracket, weakened by repeated high-stress cycling, had fractured near the deck plate weld points, causing the heavy pawl block to swing violently outboard. This rendered the primary sinkering mechanism useless. The full kinetic load of the 65,000 IWT vessel, surging forward at an estimated velocity of 10 knots relative to the seabed anchor, instantly transferred to the windlass brake. The brake, already compromised by the yielding of its retaining structure in the previous act, offered negligible resistance. The wildcat, driven by the massive momentum of the running chain, immediately began an agonizing, ear-splitting acceleration. Thompson reacted instantly. He did not run, but executed a precise, practiced move. Knowing the immediate vicinity of the running chain was a kill zone, potential for flailing links, whipping shackles, and massive thermal release, he sprinted the 2 meters to the emergency steam kill valve and the high-volume water cooling jet controls. "Jensen, brakes are gone," Thompson yelled, his voice strained but clear. He threw open the valve for the steam kill. Switch, cutting the steam supply to the engine to prevent it from seizing, and simultaneously engaged the freshwater pump line for emergency cooling. A thick jet of high-pressure water immediately struck the exterior of the rapidly spinning brake housing and wildcat. The water instantly flashed to steam, filling the forecastle deck with a dense, obscuring fog that smelled sharply of ozone and scorched grease. The speed of the chain was accelerating past safe limits. The sound was now a high-pitched metallic shriek, mixed with the rhythmic heavy clanking of the individual links hitting the wildcat pockets. It was an extremely dangerous event, a runaway wildcat. If the rotational speed became too high, the sheer mechanical forces could violently shear the chain links, or worse, cause the entire heavy wildcat casting to explode outwards. Jensen, who had been watching the stopper fail, was already beside the controls. He reached for the manual tension bar, a heavy 4-foot steel pipe designed to provide extra leverage on the brake lever mechanism. He could feel the heat radiating through the heavy leather gloves he wore. "Miller, air wrench on the tension nut. We need 5 more threads," Jensen shouted, pointing to the main tightening nut of the brake. Miller, his face white but focused, dropped the air wrench and grabbed a heavy steel hammer. The airline was useless now. They needed brute force to shear through the remaining seizing resistance. The chain was now running at a blur, a continuous gray stream of steel leaving the hawse pipe. The gauge on the brake housing pressure, now meaningless since the retaining structure had failed, was immaterial. The crucial factor was the amount of friction they could mechanically generate before the heat fused the entire mechanism. Thompson, blinded by the steam, used the sound of the chain to guide him. He knew the maximum effective range of the water jet. The cooling was critical. Chain speed of this magnitude could generate enough friction to melt the steel components in a matter of seconds. The water flow was trying to dissipate the calculated kinetic energy of a 65,000-ton vessel over a few square meters of friction surface. Jensen leaned into the manual tension bar, trying to torque the brake lever further down against the resistance of the running chain. The metal groaned in protest. He could feel the friction lining beginning to smoke visibly even through the layer of steam. The wildcat speed was peaking. The clanking of the links sounded like a high-rate machine gun. The noise was physically painful. "Pressure," Jensen yelled, putting all his weight onto the bar. He felt a slight immediate resistance. The friction lining was grabbing momentarily. Miller hammered the tightening nut aggressively, driving it down a quarter turn at a time. Each turn represented a massive increase in the clamping force on the brake band. The tension was working, but sporadically. For 5 seconds, the chain would slow slightly, the clanking deepening in tone, a good sign. Then, the immense strain from the ship surging on a wave would overcome the friction, and the wildcat would instantly accelerate, screaming louder than before. Thompson momentarily diverted the water jet to the chain itself where it entered the wildcat, hoping to cool the links and reduce the thermal expansion that was decreasing the overall effectiveness of the brake lining. The chain paid out relentlessly. Jensen glanced quickly at the markers, the link color coding for the shackles. 7 shackles were already out. They were burning through their safety margin. 8 shackles, 9 shackles. They had dropped the anchor with 7. The running chain indicated the entire length was being dragged out. Suddenly, Miller, using the extreme leverage of a long spanner and the hammer, managed to turn the nut a full, excruciating half rotation. This effort seemed to finally compress the brake band beyond its yielding point. The friction lining bit down hard. The sound instantly changed. The high-pitched scream vanished, replaced by a deep, guttural grind. The wildcat, instead of spinning freely, was now fighting a losing battle against the enormous friction. Steam billowed exponentially as the latent heat within the brake housing was violently released. The entire deck under the windlass vibrated violently. The chain speed plummeted from dangerous RPMs to a grinding crawl over about 3 seconds. "It's slowing. Keep the water on," Jensen commanded. The chain came to a full, jarring stop. The 9-shackle marker had just disappeared into the hawse pipe. The system was now holding, but at a tremendous cost. The total number of shackles out was now 10, indicating that 300 meters of chain were stretched into the deep ocean floor, far beyond the standard scope used for shelter anchoring. The silence, after the deafening roar, was absolute, broken only by the hiss of steam and the sound of the wind and the crashing waves. The immediate crisis was averted. The anchor was secured, but the damage was unknown and the position was tenuous. Jensen stepped back, letting Thompson maintain the water flow. The brake housing was visibly shimmering with intense heat, glowing a dull red beneath the layer of rust and scorched oil. They were holding on by mechanical failure, not procedure. The immediate danger had passed, but the tension on the forecastle deck remained palpable. The massive kinetic energy of the runaway chain had been converted to static friction and heat, and the resulting instability was severe. The The windlass brake housing glowed faintly, a dull cherry red, visible even through the mist of condensing steam and seawater spray. Thompson maintained the steady flow of cooling water, concentrating the jet on the brake band assembly and the wildcat segments. The objective was to bring the temperature down safely and quickly, preventing thermal distortion or the immediate cooling of stress-fractured components, which could lead to further cracking. The temperature normalization was a careful process. Too rapid cooling could be as damaging as the initial overheating. Jensen, after ensuring the brake lever was fully secured using the manual bar and the last accessible tightening nut was hammered down hard, focused on securing the chain externally. The compromised pile stopper was useless, its support frame visibly bent and detached from the deck structure. "Bosun, stop the water for 60 seconds. We need to install the emergency rig," Jensen instructed. Thompson cut the flow. The metallic hiss died down, replaced by the crackle of superheated metal contracting in the cool evening air. The crew's priority shifted to the emergency chain securing mechanism, a heavy-duty chain stopper fabricated from specialized high-tensile links and a pelican hook, designed to bear the full load of the vessel in the event of windlass failure in heavy seas. This stopper bypassed the deck-mounted pile and attached directly to a robust, reinforced structural point on the forecastle deck, securing the chain link by link. Miller and Thompson worked with urgent efficiency. Using a long steel bar, they managed to pry the anchor chain slightly away from the mangled pile stopper structure. They then inserted the first link of the emergency stopper chain into a section of the main anchor chain nearest the hawse pipe. Once aligned, Miller drove the locking pin home using a 10-pound sledgehammer, seating the emergency stopper firmly onto a central link. The final element was the tensioning. The opposite end of the emergency stopper, fitted with a hefty pelican hook, was secured to a strong point. Jensen oversaw the final cinching, using a hydraulic tensioner to ensure the emergency stopper took up all the strain, transferring the immense load from the overheated windlass brake to the structurally sound deck point. The process took 25 minutes of arduous work and the violent pitching motion. Only when the strain gauge on the hydraulic tensioner registered a significant load did Jensen authorize the full cooling recommencement. The chain is secured by the emergency stopper. The windlass is redundant, Jensen reported over the internal phone to Captain Kramer on the bridge. Captain Kramer's voice, calm and documentary, replied, "Understood, Chief Mate. Proceed with damage assessment and prepare for anchor recovery at first light, conditions permitting. Note the condition of the anchor chain and the length out." Jensen directed the crew to inspect the visible damage. The windlass brake assembly was completely compromised. The heavy steel brake band, designed to be a continuous loop, showed a distinct shear point where the retaining bolt structure had failed, likely due to fatigue exacerbated by the extreme heat. The friction material was charred and partially ejected, smelling acridly of burnt resin and metal dust. The Wildcat, though structurally intact, exhibited severe scoring and abrasion on its segments from the high-speed passage of the chain links under pressure. The deck plating around the failed pile stopper showed signs of deformation and tearing where the bolts had pulled through the steel. Thompson used an infrared thermometer to monitor the brake housing. The temperature was still settling, but the initial reading of 380 yard Cirx text Cs indicated how close they had come to a catastrophic seize-up or failure. Anchor, recovery, and lessons. Learned at 600 the following morning, the wind had dropped to a manageable force 5. Captain Kramer authorized the recovery of the anchor. The operation had to be conducted using the port windlass, which was fully operational, requiring careful cross-deck maneuvering of the secured chain, a complicated, slow, and dangerous procedure. Since the damaged starboard windlass was useless, they had to transfer the load. The port chain was secured and the starboard anchor chain was painstakingly transferred across the deck, link by link, using heavy-duty tackles and manual purchases, connecting it to the port wildcat. This process, requiring strict coordination and immense care, took nearly 3 hours. The recovery was slow and deliberate. The port windlass groaned as it began to heave against the 10 shackles, 300 meters of chain and the enormous suction of the anchor buried deep in the seabed. Thompson monitored the chain as it came in, inspecting every length for signs of stress, elongation, or deformation. At 7.5 shackles recovered, Thompson identified the critical damage point. The first 3 chain links nearest the anchor had suffered significant elongation, stretching that exceeded the maximum tolerance limit of 2%. This was characteristic of the peak dynamic load exerted on the chain during the moment the vessel surged forward uncontrollably just before the windlass. Brake completely failed. These links were permanently weakened and marked for replacement. Finally, the anchor broke the surface, its massive flukes caked in heavy mud. Jensen formally dictated the incident entry for the captain's log, maintaining the calm, factual tone required for official records. Date, time, 16/11/1978, 23:15 local. Vessel condition, anchored for shelter, force 7/8 swell. Incident, failure of starboard chain, stopper, Powell type, resulting in runaway wildcat and subsequent failure of windlass brake. Assembly, shear failure of retaining structure. Response, immediate application of manual brake tension and high-volume water cooling. Chain secured by emergency high-tensile stopper at 10 shackles out, 300 meters. Damage, starboard windlass. Wildcat scored, brake assembly totaled. Starboard chain stopper, structural deformation failure. Anchor chain, first 3 links, showing excessive elongation, requires replacement. Conclusion, incident caused by the fatigue failure of the chain stopper under repeated high-stress cycling in heavy weather. New procedural requirement, implement continuous strain gauge monitoring on all anchor securing devices in conditions above force 6. The Argonaut weighed anchor and proceeded on her course. The scarred forecastle deck a testament to the night's near disaster. The experience was logged, the lessons learned, and the necessary repairs scheduled. It was a technical failure, professionally managed, a typical hazard of maritime service in the unforgiving North Atlantic.